Hello everyone and welcome to SimpliCode's YouTube channel. I hope you guys are doing well. Today, we'll be taking you through one of the most important libraries of Python, the Scikit-Learn. Scikit-Learn is an open source machine learning library for Python that provides a range of algorithms for data mining and data analysis. It is built on top of the popular numerical computation library NumPy and is designed to integrate well with other libraries such as pandas for data processing. We have been through NumPy and pandas in the previous few videos. So with a user-friendly interface and robust performance, Scikit-Learn is a popular choice for machine learning tasks. Today, our trainer Richard will take you through all the in-depth topics of this Scikit-Learn library in Python. But before we begin, let me tell you guys that we have regular updates on multiple programming videos. So if you are a programmer and if you want to learn something new, then consider getting subscribed to our YouTube channel and press that bell icon to never miss any updates on programming videos. So without any further delay, let's hand over this session to Richard.
So what is the Scikit-Learn? It's a simple and efficient tool for data mining and data analysis. It's built on NumPy, SciPy, and Matplot library, so it interfaces very well with these other modules. And it's an open source, commercially usable BSD license. BSD originally stood for Berkeley Software Distribution License, but it means it's open source with very few restrictions as far as what you can do with it. Another reason to really like the Scikit-Learn setup, so you don't have to pay for it as a commercial license versus many other copyrighted platforms out there. What we can achieve using the Scikit-Learn, we use the two main things are classification and regression models. Classification, identifying which category an object belongs to. For one application very commonly used is spam detection. So is it a spam or is it not a spam? Yes, no. In banking, it might be, is this a good loan, bad loan? Today we'll be looking at wine. Is it going to be a good wine or a bad wine? And regression is predicting an attribute associated with an object. One example is stock prices prediction. What is going to be the next value? If the stock today sold for $23.05 a share, what do you think it's going to sell for tomorrow and the next day and the next day? So that'd be a regression model. Same thing with weather forecasting. Any of these are regression models where we're looking at one specific prediction on one attribute. Today we will be doing classification. Like I said, we're going to be looking at whether a wine's good or bad. But certainly the regression model, which is in many cases more useful because you're looking for an actual value, is also a little harder to follow sometimes. So classification is a really good place to start. We can also do clustering and model selection. Clustering is taking an automatic grouping of similar objects into sets. Customer segmentation is an example. So we have these customers like this, they'll probably also like this. Or if you like this particular kind of features on your objects, maybe you like these other objects. So a referral is a good one, especially on Amazon.com or any of your shopping networks. Model selection, comparing, validating, and choosing parameters and models. Now, this is actually a little bit deeper as far as a Scikit-Learn. We're looking at different models for predicting the right course or the best course or what's the best solution. Today, like I said, we're looking at wine, so it's going to be, well, how do you get the best wine out of this? So we can compare different models, and we'll look a little bit at that, and improve the model's accuracy via different parameters and fine-tuning. Now, this is only part one, so we're not going to do too much tuning on the models we're looking at, but I'll point them out as we go. Two other features, dimensionality reduction and pre-processing. Dimensionality reduction is we're reducing the number of random variables to consider. This increases the model efficiency. We won't touch that in today's tutorial, but be aware if you have, thousands of columns of data coming in, thousands of features, some of those are going to be duplicated, or some of them you can combine to form a new column. And by reducing all those different features into a smaller amount, you can increase the efficiency of your model. It can process faster, and in some cases you'll be less biased because if you're weighing it on the same feature over and over again, it's going to be biased to that feature. And pre-processing. These are both pre-processing, but pre-processing is feature extraction and normalization. So we're going to be transforming input data such as text for use with machine learning algorithms. We'll be doing a simple scaling in this one for our pre-processing, and I'll point that out when we get to that. And we can discuss pre-processing at that point. With that, let's go ahead and roll up our sleeves and dive in and see what we got here. Now, I like to use the Jupyter Notebook, and I use it out of the Anaconda Navigator. So if you install the Anaconda Navigator, by default, it will come with the Jupyter Notebook, or you can install the Jupyter Notebook by itself. This code will work in any of your Python setups. I believe I'm running an environment of 3.7 setup on there. I'd have to go in here into environments and look it up for the Python setup. But it's one of the 3X's. And we go ahead and launch this, and this will open it up in a web browser. So it's kind of nice. It keeps everything separate. And in this Anaconda, you can actually have different environments, different versions of Python, different modules installed in each environment. So it's a very powerful tool if you're doing a lot of development. And the Jupyter Notebook is just a wonderful visual display. Certainly you can use, I know Spider is another one which is installed with the Anaconda. I actually use a simple Notepad++ when I'm doing some of my Python script. Any of your IDEs will work fine. Jupyter Notebook is Iron Python because it's designed for the interface, but it's good to be aware of these different tools. And when I launch the Jupyter Notebook, it'll open up, like I said, a web page in here. And we'll go over here to New and create a new Python setup. And like I said, I believe this is Python 3.7, but any of the three, the Scikit-Learn works with any of the 3X's. There's even 2.7 versions. So it's been around a long time. So it's very big on the development side. And then the guys in the back, guys and gals, they went ahead and put this together for me. And let's go ahead and import our different packages. Now, if you've been reading some of our other tutorials, you'll recognize pandas as PD. Pandas library is pretty widely used. It's a data frame setup, so it's just like columns and rows in a spreadsheet with a lot of different features for looking stuff up. Seaborn sits on top of Matplot library. So this is for our graphing. And we'll see that how quick it is to throw a graph out there to view in the Jupyter Notebook for demos and showing people what's going on. And then we're going to use the random forest, the SVC or support vector classifier, and also the neural network. So we're going to look at this. We're actually going to go through and look at 3 different classifiers that are most common, some of the most common classifiers, and let's show how those work in the Scikit-Learn setup and how they're different. And then if you're going to do your setup on here, you'll want to go ahead and import some metrics. So the sklearn.metrics on here, and we're going to use the confusion metrics and the classification report out of that. And then we're going to use from the sklearn pre-processing the standard scalar and label encoder. Standard scalar is probably the most commonly used pre-processing. There's a lot of different pre-processing packages in the sklearn. And then model selection for splitting our data up. It's one of the many ways we can split data into different sections. And the last line here is our percentage matplot library inline. Some of the Seaborn and matplot library will go ahead and display perfectly inline without this, and some won't. It's good to always include this when you're in the Jupyter Notebook. This is Jupyter Notebook, so if you're in an IDE, when you run this, it'll actually open up a new window and display the graphics that way. So you only need this if you're running it in a editor like this one, with specifically Jupyter Notebook. I'm not even familiar with other editors that are like this, but I'm sure they're out there. I'm sure there's a Firefox version or something. Jupyter Notebook just happens to be the most widely used out there. And we can go ahead and hit the run button, and this now has saved all this underneath the packages. So my packages are now all loaded. I've run them, whether you run it on top or you run it to the left, and all the packages are up there, so we now have them all available to us for our project we're working on. And I'm just going to make a little side note on that. When you're playing with these and you delete something out and add something in, even if I went back and deleted this cell and just hit the scissors up here, these are still loaded in this kernel. So until I go under kernel and restart and clear or restart and run all, I'll still have access to pandas. Important to know, because I've done that before. I've loaded up, maybe not a module here, but I've loaded up my own code and then changed my mind and wondering, why does it keep putting out the wrong output? And then I realized it's still loaded in the kernel and you have to restart the kernel. Just a quick side note for working with a Jupyter Notebook and one of the troubleshooting things that comes up. And we're going to go ahead and load up our data set. We're using the pandas, so if you haven't yet, go look at our pandas tutorial. A simple read the CSV with the separation on here. And so let me go ahead and run that. And that's now loaded into the variable wine. And let's take a quick look at the actual file. I always like to look at the actual data I'm working with. In this case, we have wine quality-red. I'll just open that up. I have it in my open office setup. I'm separated by semicolons. That's important to notice. And when we open that up, you'll see we have, go all the way down here. It looks like 1,600 lines of data minus the first one, so 1,599 lines. And we have a number of features going across. The last one is quality. And right off the bat, we see the quality is has different numbers in it, 5, 6, 7. It's not really, I'm not sure how high of a level it goes, but I don't see anything over a 7. So it's kind of 5 through 7 is what I see here. 5, 6, and 7. 4, 5, 6, and 7. Looking to see if there's any other values in there. Looking through the demo to begin with, I didn't realize the setup on this. So you can see there's the different quality values in there: alcohol, sulfates, pH, density, total sulfur dioxide, and so on. Those are all the features we're going to be looking at. And since this is a pandas, we'll just do wine head, and that prints the first 5 rows of data. That's of course a pandas command. And we can see that looks very similar to what we were looking at before. We have everything across here. It's automatically assigned an index on the left. That's what pandas does if you don't give it an index. And for the column names, it has assigned the first row. So we have our first row of data pulled off our comma separated variable file, in this case semicolon separated. And it shows the different features going across. And we have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 features. 12 including quality, but that's the one we want to work on and understand. And then because we're in pandas data frame, we can also do wine.info. And let's go ahead and run that. This tells us a lot about our variables we're working with. You'll see here that there is 1,599. That's what I said from the spreadsheet, so that looks correct. Non-null float 64. This is very important information, especially the non-null. So there's no null values in here. That can really trip us up in pre-processing. And there's a number of ways to process non-null values. One is just to delete that data out of there. So if you have enough data in there, you might just delete your non-null values. Another one is to fill that information in with like the average or the most common values or other such means. But we're not going to have to worry about that. But we'll look at another way, because we can also do wine is null and sum it up. And this will give us a similar, it won't tell us that these are float values, but it will give us a summation. Oops, there we go, let me run that. It'll give us a summation on here, how many null values in each one. So if you wanted to, from here you would be able to say, okay, this is a null value, but it doesn't tell you how many are null values. This one would clearly tell you that you have maybe 5 null values here, 2 null values here. And you might just, if you had only 7 null values and all that different data, you'd probably just delete them out. Where if 90% of the data was null values, you might rethink either a different data collection setup or find a different way to deal with the null values. And we'll talk about that just a little bit in the models too, because the models themselves have some built-in features, especially the forest model, which we're going to look at. At this point, we need to make a choice. And to keep it simple, we're going to do a little pre-processing of the data, and we're going to create some bins. And bins we're going to do is 2, 6.5, 8. What this means is that we're going to take those values. If you remember up here, let me just scroll back up here. We had our quality. The quality comes out between 2 and 8 basically, or 1 and 8. But we have 5, 5, 5, 6. You can see just in the first 5 lines of variation in quality. We're going to separate that into just 2 bins of quality. And so we've decided to create 2 bins. We have bad and good. It's going to be the labels on those 2 bins. We have a spread of 6.5 and an exact index of 8. The exact index is because we're doing 0 to 8 on there. The 6.5 we can change. We could actually make this smaller or greater, but we're only looking for the really good wine. We're not looking for the 0, 1, 2, 3, 4, 5, 6. We're looking for wines with 7 or 8 on them. So high quality. This is what I want to put on my dinner table at night. I want to taste the good wine, not the semi-good wine or mediocre wine. And then this is a pandas. So PD, remember, stands for pandas. Pandas cut means we're cutting out the wine quality and we're replacing it. And then we have our bins equals bins. That's the command. Bins is the actual command. And then our variable bins, 2, 6.58. So 2 different bins. And our labels, bad and good. And we can also do, let me just do it this way. Wine quality, since that's what we're working on. And let's look at unique. Another pandas command, and we'll run this. And I get this lovely error. Why did I get an error? Well, because I replaced wine quality and I did this cut here, which changes things on here. So I literally altered one of the variables that is saved in the memory. So we'll go up here to the kernel, restart and run all. That starts it from the very beginning. And we can see here that that fixes the error because I'm not cutting something that's already been cut. We have our wine quality unique, and the wine quality unique is a bad or good. So we have 2 qualities objects. Bad is less than good, meaning bad's going to be 0 and good's going to be 1. And to make that happen, we need to actually encode it. So we'll use the label quality equals label encoder. And the label encoder, let me just go back there since this is part of Scikit-Learn. That was one of the things we imported, was a label encoder. You can see that right here from the Scikit-Learn.processing import standard scalar, which we're going to use in a minute, and label encoder. And that's what tells it to use bad equals 0 and good equals 1. And we'll go ahead and run that, and then we need to apply it to the data. And when we do that, we take our wine quality that we had before, and we're going to set that equal to label quality, which is our encoder. And let's look at this line right here. We have dot fit transform. And you'll see this in the pre-processing. These are the most common used, is fit transform and fit transform. Because they're so often that you're also transforming the data, when you fit it, they just combine them into one command. And we're just going to take the wine quality, feed it back into there, and put that back in our wine quality setup, and run that. And now when we do the wine and the head of the first 5 values, and we go ahead and run this, you can see right here underneath quality 0, 0, 0. I have to go down a little further to look at the better wines. Let's see if we have some that are ones. Yeah, there we go. There's some ones down here. So when we look at 10 of them, you can see all the way down to 0 or 1. That's our quality. And again, we're looking at high quality. We're looking at the 7 and the 8s, or 6.5 and up. And let's go ahead and grab our, where was it? Here we go, wine quality. And let's take another look at what else, more information about the wine quality itself. And we can do a simple pandas thing, value counts. Hopefully I typed that in there correctly. And we can see that we only have 217 of our wines which are going to be the higher quality. So 217, and the rest of them fall into the bad bucket, the 0, which is 1,382. So again, we're just looking for the top percentage of these. The top, what is that? It's probably about a little under 20% on there. So we're looking for our top wines, our 7 and 8s. And let's use our, let's plot this on a graph so we can take a look at this. And the SNS, if you remember correctly, that is, let me just go back to the top, that's our seaborn. Seaborn sits on top of Matplot library. It has a lot of added features, plus all the features of the Matplot library, and it also makes it quick and easy to put out a graph. And we'll do a simple bar graph, and they actually call it count plot. And then we want to just do count plot the wine quality. So let's put our wine quality in there. And let's go ahead and run this and see what that looks like. And nice inline. Remember, this is why we did the inline, so make sure it appears in here. And you can see the blue space, or the first space, represents low quality wine, and our second bar is a high quality line. And you can see that we're just looking at the top quality wine here. Most of the wine, we want to just give it away to the neighbors. No, maybe if you don't like your neighbors. Maybe give them the good quality wine, and I don't know what you do with the bad quality wine. I guess use it for cooking. There we go. But you can see here it forms a nice little graph for us with the seaborn on there, and you can see our setup on that. So now we've done some pre-processing. We've described our data a little bit. We have a picture of how much of the wine, what we expect it to be, high quality, low quality. Checked out the fact that there's none, we don't have any null values to contend with or any odd values. Some of the other things you sometimes look at these is if you have like some values that are just way off the chart. So the measurement might be off, or miscalibrated equipment if you're in the scientific field. So the next step we want to go ahead and do is we want to go ahead and separate our data set, or reformat our data set. And we usually use capital X, and that denotes the features we're working with. And we usually use a lowercase y. That denotes what, in this case, quality, what we're looking for. And we can take this and we can go wine. It's going to be our full thing of wine. Dropping, what are we dropping? We're dropping the quality. So these are all the features minus quality. And make sure we have our axes equals 1. If you left it out, it would still come out correctly just because of the way it processes on the defaults. And then our y, if we're going to remove quality for our x, that's just going to be wine, and it is just the quality that we're looking at for y. So we put that in there. And we'll go ahead and run this. So now we've separated the features that we want to use to predict the quality of the wine and the quality itself. The next step is if you're going to create a data set and a model, we got to know how good our model is. So we're going to split the data, train and test splitting data. And this is one of the packages we imported from Scikit-Learn. And the actual package was train, test, split. And we're going to do x, y, test size 0.2, random state 42. And this returns 4 variables. And most common you'll see is capital X train, so we're going to train our set with. Capital X test, that's the data we're going to keep on the side to test it with. Y train, Y remember stands for the quality or the answer we're looking for. So when we train it, we're going to use X train and Y train, and then Y test to see how good our X test does. And the train test split, let me just go back up to the top. That was part of the Scikit-Learn model selection, import train test split. There is a lot of ways to split data up. This is, when you're first starting, you do your first model, you probably start with the basics on here. You have one test for training, one for test. Our test size is 0.2 or 20%. And random state just means we just start with it's like a random seed number, so it's not too important back there. We're randomly selecting which ones we're going to use. Since this is the most common way, this is what we're going to use today. There is, and it's not even an Scikit-Learn package yet, so someone's still putting it in there. One of the new things they do is they split the data into thirds, and then they'll run the model on they combine each of those thirds into 2 thirds for training and 1 for testing. And so you actually go through all the data and you come up with 3 different test results from it, which is pretty cool. That's a pretty cool way of doing it. You could actually do that with this by just splitting this into thirds, and then, or have a one test set third, and then split the training set also into thirds, and also do that and get 3 different data sets. This works fine for most projects, especially when you're starting out. It works great. So we have our X train, our X test, our Y train, and our Y test. And then we need to go ahead and do the scalar. And let's talk about this because this is really important. Some models do not need to have scaling going on. Most models do. And so we create our scalar variable. We'll call it SC, standard scalar. And if you remember correctly, we imported that here, along with the label encoder, the standard scalar setup. So there's our scalar, and this is going to convert the values. Instead of having some values that go from 0, if you remember up here we had some values are 54, 60, 40, 59, 102. So our total sulfur dioxide would have these huge values coming into our model. And some models would look at that and they'd become very biased to sulfur dioxide. It'd have the hugest impact. And then a value that had 0.076, 0.098, or chlorides would have very little impact because it's such a small number. So when we take the scalar, we kind of level the playing field. And depending on our scalar, it sets it up between 0 and 1 a lot of times is what it does. Let's go ahead and take a look at that. And we'll go ahead and start with our X train. And our X train equals SC fit transform. We talked about that earlier. That's an Scikit-Learn setup. It's going to both fit and transform our X train into our X train variable. And if we have an X train, we also need to do that to our test. And this is important because you need to note that you don't want to refit the data. We want to use the same fit we used on the training as on the testing. Otherwise, you get different results. And so we'll do just, oops, not fit, transform. We're only going to transform the test side of the data. So here's our X test that we want to transform. And let's go ahead and run that. And just so we have an idea, let's go ahead and take and just print out our X train. Oh, let's do first 10 variables, very similar to the way you do the head on a data frame. You can see here our variables are now much more uniform, and they've scaled them to the same scale, so they're between certain numbers. And with the basic scalar, you can fine-tune it. I just let it do its defaults on this, and that's fine for what we're doing. In most cases, you don't really need to mess with it too much. It does look like it goes between like probably -2 to 2 or something like that. That's just looking at the train variable. We'll go ahead and cut that one out of there. So before we actually build the models and start discussing the Scikit-Learn models we're going to use, we covered a lot of ground here. When you're working with these models, you put a lot of work into prepping the data. So we looked at the data, noticed that it's separated, loaded it up. We went in there, we found out there's no null values. That's hard to say, no null values. We have, there's none null value. I can't say it. And of course we sum it up. If you had a lot of null values, this would be really important coming in here. So is there a null summary? We looked at pre-processing the data as far as the quality. And we're looking at the bins. So this would be something you might start playing with. Maybe you don't want super fine wine. You don't want the 7 and 8s. Maybe you want to split this differently. So certainly you can play with the bins and get different values and make the bins smaller or lean more towards the lower quality. So you then have like medium to high quality. And we went ahead and gave it labels. Again, this is all pandas we're doing in here. Setting it up with unique labels and group names. Bad, good. Bad is less than good. That can be so important. You don't know how many times people go through these models and they have them reversed or something. And then they go back and they're like, why is this data not looking correct? So it's important to remember what you're doing up here and double check it. And we used our label encoder. So that was to set that up as quality 0, 1. Good, in this case we have bad, good, 0, 1. And we just double check that to make sure that's what came up in the quality there. And then we threw it into a graph because people like to see graphs. I don't know about you, but you start looking at all these numbers and all this text, and you get down here and you say, oh, yes, here, this is how much of the wine we're going to label as subpar, not good. And this is how much we're going to label as good. And then we got down here to finally separating out our data so it's ready to go into the models. And the models take X and a Y. In this case, X is all of our features minus the one we're looking for, and then Y is the features we're looking for. So in this case, we dropped quality, and in the Y case, we added quality. And then because we need to have a training set and a test set so we can see how good our models do, we went ahead and split the models up, X-train, X-test, Y-train, Y-test. And that's using the train test split, which is part of the sklearn package. And we did, as far as our testing size, 0.2 or 20%. The default is 25%, so if you leave that out, it'll do default setup. And we did a random state equals 42. If you leave that out, it'll use a random state. I believe it's default 1. I'd have to look that back up. And then finally, we scaled the data. This is so important to scale the data. Going back up to here, if you have something that's coming out as 100, it's going to really outweigh something that's 0.071. That's not in all the models. Different models handle it differently. And as we look at the different models, I'll talk a little bit about that. We're going to only look at 3 models today, 3 of the top models used for this, and see how they compare and how the numbers come out between them. So we're going to look at 3 different setups. Oh, let me change my cell here to markdown. There we go. And we're going to start with the random forest classifier. So the 3 setups we're looking at is the random forest classifier, support vector classifier, and then a neural network. Now we start with the random forest classifier because it has the least amount of moving parts to fine tune. And let's go ahead and put this in here. So we're going to call it RFC for random forest classifier. And if you remember, we imported that. So let me go back up here to the top real quick. And we did an import of the random forest classifier from sklearn ensemble. And then we also, let me just point this out. Here's our SVM where we imported our support vector classifier. So SVM is support vector model, support vector classifier. And then we also have our neural network. And we're going to, from there, the multi-layered perceptron classifier. Kind of a mouthful for the P, perceptron. Don't worry too much about that name. It's a neural network. There's a lot of different options on there in setups, which is where they came up with the perceptron. So we have our 3 different models we're going to go through on here. And then we're going to weigh them. Here's our metrics. So we're going to use a confusion metrics, also from the sklearn package, to see how good our model does with our split. So let's go back down there and take a look at that. And we have our RFS equals random forest classifier, and we have n estimators equals 200. This is the only value you play with a random forest classifier. How many forests do you need? Or how many trees in the forest? So how many models are in here? That makes it pretty good as a startup model because we're only playing with one number and it's pretty clear what it is, and you can lower this number or raise it. Usually start up with a higher number and then bring it down to see if it keeps the same value. So you have less, the smaller the model, the better the fit, and it's easier to send out to somebody else if you're going to distribute it. Now the random forest classifier, everything I read says it's used for kind of a medium-sized data set. So you can run it on big data, you can run it on smaller data obviously, but it tends to work best in the mid-range. And we'll go ahead and take our RFC, and I just copied this from the other side, .fit xtrain, y-train. So we're sending it our features and then the quality in the Y-train, what we want to predict in there. And we just do a simple fit. Now remember, this is sklearn, so everything is fit or transform. Another one is predict, which we'll do in just a second here. In fact, let's do that now. Predict RFC equals, and it's our RFC model, predict. And what are we predicting on? Well, we trained it with our train values, so now we need our test, our X test. So this has done it. This is the 3 lanes of code we need to create our random forest variable, fit our training data to it. So we're programming it to fit. In this case, it's got 200 different trees it's going to build. And then we're going to predict on here. And let me go ahead and just run that. And we can actually do something like, let's do predict RFC. Just real quick, we'll look at the first 20 variables of it. Let's go ahead and run that. And in our first 20 variables, we have 3 wines that make the cut, and the other 17 don't. So the other 17 are bad quality, and 3 of them are good quality in our predicted values. And if you can remember correctly, we'll go ahead and take this out of here. This is based on our test. So these are the first 20 values in our test, and this has, as you can see, all the different features listed in there, and they've been scaled. So when you look at these, they're a little bit confusing to look at and hard to read, but we have, there's a minus 0.01, so this is 0.36, minus 0.01, so 0.164, minus 0.09, or no, it's still minus 1, so minus 0.9, all between 0 and 1 on here. I think I was confused earlier and I said 0 between 2, negative 2, but it's between minus 1 and 1, which is what it should be in the scale. And we'll go ahead and just cut that out of there. Run this. We have our setup on here. So now that we've run the prediction and we have predicted values, well, one, you could publish them, but what do we do with them? Well, what we want to do with them is we want to see how well our model performed. That's the whole reason for splitting it between a training and testing model. And for that, if you remember, we imported the classification report. That was again from the Scikit-Learn. There's our confusion matrix and classification report. And the classification report actually sits on the confusion matrix, so it uses that information. And our classification report, we want to know how good our Y test, that's the actual values, versus our predicted RFC. So we'll go ahead and print this report out, and let's take a look. And we can see here we have a precision out of the 0. We had about 0.92 that were labeled as bad that were actually bad. And out of precision for the quality wines, we're running about 78%. So you kind of give us an overall 90%. And you can see our F1 score, our support set up on there, our recall. You could also do the confusion matrix on here, which gives you a little bit more information. But for this is going to be good enough for right now. We're just going to look at how good this model was, because we want to compare the random forest classifier with the other 2 models. And you know what, let's go ahead and put in the confusion matrix, just so you can see that on there, with Y-test and prediction RFC. So in the confusion matrix, we can see here that we had 266 correct and 7 wrong. These are the mislabels for bad wine, and we had a lot of mislabels for good wine. So our quality labels aren't that good. We're good at predicting bad wine, not so good at predicting whether it's a good quality wine. Important to note on there. So that is our basic random forest classifier. And let me go ahead, change cell type to markdown and run that so we have a nice label. Let's look at our SVM classifier, our support vector model. And this should look familiar. We have our CLF we're going to create. We'll call it, just like we called this an RFC. And then we'll have our CLF.fit. And this should be identical to up above. X train, comma, Y train. And just like we did before, let's go ahead and do the prediction. And here is our CLF predict. And it's going to equal the CLF.predict. And we want to go ahead and use X underscore test. And right about now you can realize that you can create these different models and actually just create a loop to go through your different models and put the data in. And that's how they designed it. They designed it to have that ability. Let's go ahead and run this, and then let's go ahead and do our classification report. And I'm just going to copy this right off of here. They say you shouldn't copy and paste your code, and the reason is when you go in here and edit it, you invariably will miss something. We only have 2 lines, so I think I'm safe to do it today. And let's go ahead and run this. And let's take a look how the SVM classifier came out. So up here we had a 90%, and down here we're running about an 86%. So it's not doing as good. Now remember, we randomly split the data, so if I run this a bunch of times, you'll see some changes down here. So these numbers, this size of data, if I ran it 100 times, it would probably be within plus or minus 3 or 4 on here. In fact, if I ran this 100 times, you'd probably see these come out almost the same as far as how well they do in classification. And then on the confusion matrix, let's take a look at this one. This had 22 by 25. This one has 35 by 12. So it's doing not quite as good. That shows up here 71% versus 78%. And then if we're going to do a SVM classifier, we also want to show you one more. And before I do that, kind of tease you a little bit here, before we jump into neural networks, the big save all deep learning, because everything else must be shallow learning, that's a joke. Let's just talk a little bit about the SVM versus the random forest classifier. The SVM tends to work better on smaller numbers. It also works really good on, because a lot of times you convert things into numbers and bins and things like that. The random forest tends to do better with those. At least that's my brief experience with it. Where if you have just a lot of raw data coming in, the SVM is usually the fastest and easiest to apply model on there. So they each have their own benefits. You'll find though again that when you run these like 100 times, the difference between these two on a data set like this is going to just go away. There's randomness involved depending on which data we took and how they classify them. The big one is the neural networks, and this is what makes the neural networks nice is they can look into huge amounts of data. So for a project like this, you probably don't need a neural network on this, but it's important to see how they work differently and how they come up differently. So you can work with huge amounts of data. You can also, in many respects, they work really good with text analysis, especially if it's time sensitive. More and more you have an order of text, and they've just come out with different ways of feeding that data in, where the series and the order of the words is really important. Same thing with starting to predict in the stock market. If you have tons of data coming in from different sources, the neural network can really process that in a powerful way to pull up things that aren't seen before. And when I say lots of data coming in, I'm not talking about just the high lows that you can run an SVM on real easily. I'm talking about the data that comes in where you have maybe you pulled off the Twitter feeds and have word counts going on, and you've pulled off the different news feeds that business are looking at, and the different releases when they release the different reports. So you have all this different data coming in, and the neural network does really good with that. Pictures. Picture processing now is really moving heavily into the neural network. If you have a Pixel 2 or Pixel 3 phone put out by Google, it has a neural network for doing, it's kind of goofy, but you can put little Star Wars androids dancing around your pictures and things like that. That's all done with the neural network. So it has a lot of different uses, but it's also requires a lot of data and is a little heavy-handed for something like this. And this should now look familiar because we've done it twice before. We have our multi-layered perceptron classifier. We'll call it an MLPC, and it's this is what we imported, MLPC classifier. There's a lot of settings in here. The first one is the hidden layers. You have to have the hidden layers in there. We're going to do 3 layers of 11 each. So that's how many nodes are in each layer as it comes in. And that was based on the fact we have 11 features coming in. Then I went ahead and just did 3 layers. Probably get by with a lot less on this. But I didn't want to sit and play with it all afternoon. Again, this is one of those things you play with a lot because the more hidden layers you have, the more resources you're using. You can also run into problems with overfitting, with too many layers, and you also have to run higher iterations. The max iteration we have is set to 500. The default's 200. Because I use 3 layers of 11 each, which is, by the way, kind of a default I use. I realized that usually you have about 3 layers going down and the number of features going across. You'll see that's pretty common for the first classifier when you're working in neural networks. But it also means you have to do higher iterations. So we up the iterations to 500. So that means it's going through the data 500 times to program those different layers and carefully adjust them. And we do have a full tutorials you can go look up on neural networks and understand the neural network settings a lot more. And of course we have, you're looking over here where we had our previous model where we fit it. Same thing here, MLPC, fit, X train, Y train. And then we're going to create our prediction. So let's do our predict and MLPC, and it's going to equal the MLPC. And we'll just take the same thing here, predict X test. Let's just put that down here, dot predict X test. And if I run that, we've now programmed it. We now have our prediction here, same as before. And we'll go ahead and do the copy print again. Always be careful with the copy paste, because you always run the chance of missing one of these variables. So if you're doing a lot of coding, you might want to skip that copy and paste and just type it in. And let's go ahead and run this and see what that looks like. And we came up with an 88%. We're going to compare that with the 86 from our tree, our SVM classifier, and our 90 from the random forest classifier. And keep in mind, random forest classifiers, they do good on mid-sized data. The SVM on smaller amounts of data, although to be honest, I don't think that's necessarily the split between the two. And these things will actually come together if you ran them a number of times. And we can see down here the amount of good wines mislabeled with setup on there. It's on par with our random forest. So it had 22, 25. Shouldn't be a surprise, it's identical. It just didn't do as good with the bad wines labeling, what's a bad wine and what's not. See, yeah, because they had 266 and 7. We had down here 260 and 13. So it mislabeled a couple of the bad wines as good wines. So we've explored 3 of these basic classifiers. These are probably the 3 most widely used right now. I might even throw in the random tree. If we open up their website and we go under supervised learning, there's a linear model. We didn't do that. Most of the data usually just start with a linear model because it's going to process the quickest and use the least amount of resources. But you can see they have linear quadratic, they have kernel ridge. There's our support vector, stochastic gradient, nearest neighbors. Nearest neighbors is another common one that's used a lot. Very similar to the SVM. Gaussian process, cross decomposition, naive Bayes. This is more of an intellectual one that I don't see used a lot, but it's like the basis of a lot of other things. Decision tree, there's another one that's used a lot. Ensemble methods, not as much. Multi-class and multi-label algorithms, feature selection, neural networks, that's the other one we use down here, and of course the forest. So you can see there's in sklearn there are so many different options, and they've just developed them over the years. We covered 3 of the most commonly used ones in here and went over a little bit over why they're different. Neural network, just because it's fun to work in deep learning and not in shallow learning, as I told you. That doesn't mean that the SVM is actually shallow. It covers a lot of things, and same thing with the decision tree, the random forest classifier. And we notice that there's a number of other different classifier options in there. These are just the 3 most common ones, and I'd probably throw the nearest neighbor in there and the decision tree, which is usually part of the decision forest depending on what the backend you're using. And since, as human beings, if I was in the shareholder's office, I wouldn't want to leave them with a confusion matrix. They need that information for making decisions, but we want to give them just one particular score. And so I would go ahead and we have our sklearn metrics. We're going to import the accuracy score, and I'm just going to do this on the random forest since that was our best model. And we have our CM accuracy score, and I forgot to print it. If you remember in Jupyter Notebook, we can just do the last variable we leave out there, it'll print. And so our CM accuracy score we get is 90%. And that matches up here. We should already see that up here in precision. So you can either quote that, but a lot of times people like to see it highlighted at the very end. This is our precision on this model. And then the final stage is we would like to use this for future. So let's go ahead and take our wine. If you remember correctly, we'll do wine head of 10. We'll run that. Remember our original data set? We've gone through so many steps. Now we're going to go back to the original data. And we can see here we have our top 10 on the list. Only 2 of them make it as having high enough quality wine for us to be interested in them. And then let's go ahead and create some data here. We'll call it x new equals, and this is important. This data has to be, we just kind of randomly selected some data. It looks an awful lot like some of the other numbers on here, which is what it should look like. And so we have our x new equals 7.3.58. and so on. And then it is so important. This is where people forget this step. X new equals SC. Remember SC? That was our standard scalar variable we created. If we go right back up here, before we did anything else, we created an SC, we fit it, and we transformed it, and then we need to do what? Transform the data we're going to feed in. So we're going to go back down here, and we're going to transform our X new, and then we were going to go ahead and use the, where are we at? Here we go. Our random forest, and if you remember, all it is our RFC predict model right there. Let's go ahead and just grab that down here. And so our Y new equals, here's our RFC predict. We're going to do our X new in, and then it's kind of nice to know what it actually puts out. So according to this, it should print out what our prediction is for this wine. And, oh, it's a bad wine. Okay, so we didn't pick out a good wine for our X new. And that should be expected. Most of the wine, if you remember correctly, only a small percentage of the wine met our quality requirements. So we can look at this and say, oh, we'll have to try another wine out, which is fine by me because I like to try out new wines, and I certainly have a collection of old wine bottles, and very few of them match. But you can see here we've gone through the whole process. Just a quick rehash. We had our imports. We touched a lot on the sklearn, our random forest, our SVM, and our MLP classifier. So we had our support vector classifier, we had our random forest, and we have our neural network, 3 of the top used classifiers in the sklearn system. And we also have our confusion matrix and our classification report, which we used, our standard scaler for scaling it, and our label encoder. And of course, we needed to go ahead and split our data up in our mplot line train. And we explored the data in here for null values. We set up our quality into bins. We took a look at the data and what we actually have and put a nice little plot to show our quality, what we're looking at. And then we went through our 3 different models. And it's always interesting because you spend so much time getting to these models, and then you kind of go through the models and play with them until you get the best training on there without becoming biased. That's always a challenge, is to not overtrain your data to the point where you're training it to fit the test value. And finally, we went ahead and actually used it and applied it to a new wine, which unfortunately didn't make the cut. It's going to be the one that we drink a glass out of and save the rest for cooking. Of course, that's according to the random forest on there, because we used the best model that it came up with.
And with that, we have come to the end of this Python scikit tutorial. I hope you guys must have got a good idea about what scikit library in Python is and how we can use it in Python. If you still have any doubts related to any of the topics we have covered in this particular video, then please feel free to drop them down in the comment section below, and our experts will definitely answer them for you. Thank you so much for being here, guys. See you next time with some another video. Until then, keep coding and stay tuned to SimpliCode.